Background and history of dark matter. In the 1930s, Fritz Zwicky, a Swiss astronomer, noticed something peculiar while observing the Coma cluster of galaxies. He observed that the galaxies were moving way too fast, so fast that they would be flying apart from each other because all those stars and clusters would have too less gravity to hold it all together. Zwicky thought that there must be some invisible force holding the universe together. He named it dark matter. In our solar system, the innermost planet moves the fastest and the outermost planet moves the slowest, since the harder you push or pull on something, the faster it moves, and the sun's gravity would decrease with the increasing distance. In the 1970s, Vera Rubin studied our neighboring galaxy, the Andromeda Galaxy, and discovered that the planetary bodies were obeying no such rule. In fact, they all were moving at the same constant speed. After this observation, she decided to survey 60 other galaxies and noticed they all seemed to violate the law of gravity. She discovered that there was some force making everything go faster, which was dark matter.
So what is dark matter? I'll be elaborating on what Path said, but from a more mathematical point of view. The Earth travels in an elliptical orbit around the Sun. This means that at certain points of the year it's closer to the Sun and at certain points it's further away. However, we can assume it's traveling in a perfect circular orbit. This allows us to say that the Earth has a centripetal acceleration, which is equal to its orbital velocity squared divided by the distance from the Sun. Using Newton's second law of motion, F equals ma, we can multiply the centripetal acceleration of the Earth by its mass to give the centripetal force. We can equate this to the gravitational force, and after solving for v, the orbital velocity of the Earth, we get that it is equal to the square root of the gravitational constant multiplied by the mass of the Sun divided by the distance. As you can see, the mass of the Earth plays no role here, and thus the orbital velocity of a planet or any planet is independent of its mass. If we were to plot the orbital velocity of each planet against its distance from the Sun, we get a graph, or the rotation curve of the solar system, that looks like this. It's a decreasing exponential curve. This means that the time it takes for the Earth to orbit the Sun is 1 year, whereas for Neptune, it's about 160 years. Vera Rubin thought that this should also apply to bigger structures like galaxies. So she measured the orbital velocity of stars towards the center of a galaxy and compared it to the orbital velocity of stars towards the edge of the galaxy, and found that they actually traveled at the same rate. This means that there had to be additional mass unaccounted for. This led to two main theories: the theory of dark matter and modified Newtonian dynamics, also known as MOND. So what exactly is dark matter? Dark matter is sort of like a halo that envelops structures like galaxies. It gives additional mass to these galaxies, which help retain their shape and structure. We know it's there, we just can't see it.
Modified Newtonian dynamics. MOND is a hypothesis proposing a modification of Newton's laws of motion to account for the observed properties of galaxies. It attempts to explain why galaxies don't appear to obey the current laws of physics. Two schools of thought with the rotation curve are new substance that has mass and is pulling and making stars move quickly, that is dark matter, and gravity on the galactic scale works differently on the scale of the planet, modified Newtonian dynamics. The relation between dark matter and MOND. MOND. This theory's original intent was to explain why the dark matter makes the galaxies defy the original laws of gravity. That is, by acknowledging that the velocities of these galaxies is larger than expected to be according to Newtonian mechanics. Dark matter, the only way through which the dark matter exists is by noticing the gravitational effect it has on planetary bodies, but it still defies our concepts. Therefore, in order to explain the existence of dark matter, MOND was created.
So why is MOND not as popular as dark matter? This is for two main reasons. The first reason is that it isn't as complete as dark matter. It isn't able to create a successful cosmological model as dark matter has been able to. And the second reason is that upon analysis of the MOND theory, it turns out that for part of it to work, dark matter has to actually exist. Now, while dark matter is the current supported theory, the MOND theory is constantly revised, coming up with new formulas and alterations based on incoming data. So as of now, we can't say which model is the correct one. However, currently, the most accurate theory is the one of dark matter.
Hi, my name is Abrar, and I'll be talking about the applications of dark matter. So, the discovery of dark matter will one day undoubtedly be tremendous. If we are able to detect dark matter, many other pieces of the puzzle, that is physics, can be discovered. While the discovery itself may have many applications in the world, the time leading up to the discovery will also have an effect. That is, dark matter will indirectly affect many other aspects of science. The machines and technology that we develop to one day detect dark matter may also be able to detect other types of matter, as they need to be very sensitive. Professor Long gave us a good example. Dark matter detectors can be used to see if nuclear bombs are being tested or fired. The same detectors that detect dark matter are able to detect neutrinos, a result of nuclear explosions. These machines double as dark matter detectors, but also as means of keeping watch on countries to see if they have detonated any nuclear bombs. Another benefit of this sensitivity is the ability to detect very tiny changes or signals. For example, in the CREST dark matter search, the detectors were able to give the best data on microfractures in sapphire crystals. This data in turn led to a better understanding on how microfractures themselves worked. Another form of dark matter detectors, known as cryodetectors, can help boost the sensitivity of mass spectrometers, which in turn are used to study large biological molecules. This is possible because those cryodetectors can measure the tiniest amount of energy that dark matter would give off to normal matter. Besides those, the discovery of dark matter itself will also have many applications in the world. If one day we are able to harness the power of dark matter, it would be amazing. It's not rare, but rather one of the most abundant types of matter in the universe. More of it is in the universe than normal matter. Another great thing about dark matter is that it isn't in some faraway place. It's in the same room as us, just whizzing around and not interacting with anything. If we are able to capture and liberate the energy that's within the dark matter, we could essentially be very powerful. Dark matter being so convenient as well as being so abundant makes it a very useful type of matter to harness.